In this video, we are going to see constraint optimization algorithms. So we'll begin with equality constraint algorithms. Um, there are some certain standard ways of dealing with these problems. So we know how to solve an unconstrained optimization problem. So what we do is some standard ways. One of them that we'll see is elimination of the constraints. We'll eliminate the constraints and frame an equivalent problem and solve it, or we can solve the dual problem. Dual problem turns out to be an unconstrained problem in some cases. So if we can exploit that, that is one way of doing it. So these two are sort of small discussions in this video. The bigger discussion uh, will be the extension of Newton's method for constrained case. So we'll see elimination of the constraints first. Suppose our problem is this: minimize subject to ax equal to b, and we have to eliminate our constraint ax equal to b, and we want to fix this constraint into the problem. uh, I think we have seen this in one of our previous videos, where we introduce we introduce another matrix f such that um, f uh, range of f is equal to null space of a, and uh, and we solve this problem. Introduce f and we solve this problem. um, the problem we solve is minimize f of fz plus x hat, where x hat is a particular solution of ax equal to b. Now, why does it make sense to do this? It makes sense because fz plus x hat, this vector, due to the construction of f in this way, fz plus x hat will be in the feasible set of our problem 1. So we can have x as fz plus x hat. We can see this like a of fz plus x hat will be af z plus ax hat, and this is 0 and this is b. So whatever value we take for, so all the values which are like fz plus x hat, they will be in the feasible set of our problem 1. So minimizing over this feasible set is equivalent to minimizing over fz plus x hat, minimizing our same function over fz plus x hat. It will give the same optimal value. So when we do this minimization, we get some z star, the point which optimizes, the optimizer of this function f is z star. So we can trace back x star as uh, f of z star plus x hat, like this. So let me write it down. um, if z star is the minimizer of fz plus x hat, then x star equal to fz star plus x hat is the solution of problem 1. This is problem 1. Okay, so the dual optimal for this problem will be nu star equals minus a transpose a del of fx star. So to see that this is actually the dual optimal, we may use our KKT conditions, which for equality constraint problems, our KKT conditions is the primal feasibility condition and the derivative condition. So the derivative condition is uh, del f x star plus a transpose nu star equal to 0. This should hold. So basically I'll write this like this. So my claim is that this thing is an optimal, this is the dual optimal. um, and I'm proving my claim. So to prove my claim, I use the KKT conditions for equality constraint problems, which is this, and I just need to substitute nu star and see that this is actually 0. So this should hold true. This should hold true. So a transpose minus a transpose a del fixed star should hold true. Like this should hold true. So I'll write it like ISTPT. It is sufficient to prove that. Okay, so to see that this thing actually holds true, uh, we'll use the fact that we have f. So we use this matrix f transpose A, and since null space of A is equal to range of f, this matrix has to be full rank. So if this matrix is full rank and we have to prove that this is 0, we can just multiply them and see that um, this is indeed 0. The product is 0, and the product is 0 only when this term is 0. So the product, the top block is like f transpose times this entire term. So we have f transpose times del fx star plus a transpose a transpose inverse a del fx star. So we have f transpose a transpose here, so this is f transpose plus f transpose a transpose, and this is af transpose, and that is 0 because of this relation. So this term is 0, and we have left with f transpose times del fx star, which is del of f fz star plus x hat. This is just the chain rule expansion of the RHS is the chain rule expansion of the RHS, and this is the derivative at the optimal point, which is 0 of an unconstrained problem. So it is 0. So the top block is 0, and the bottom block, so we have the top block as top block was this thing, if transpose times this term, it was 0, and the bottom block is a times this term, and what is that? So that will be a times del fx star plus, rather, a transpose minus a transpose inverse a del fx star. So this is just identity, this negative sign will come here, this is just identity, so it is gone, and we have left with these two terms which are the same, so they cancel out and give 0. So this is also 0, so the bottom block is also 0. So we have this f transpose a times whatever we have written here is 0 0, and since we know that f transpose a is full rank, so this term has to be 0. So we are done. To solving via the dual. Solving via the dual. So we have the same problem. We have minimize fx subject to ax equal to b, and we write down the Lagrangian, frame the dual. So it's new f of x plus new transpose ax minus b. So my g of new is infimum over x fx plus new transpose ax minus new transpose b, which is minus new transpose b, minus new transpose b plus infimum over x f of x plus new transpose ax, and this is sort of um, or this term is closely related to the conjugate. This is just minus supreme over x minus fx minus new transpose x. We just push that, we just change the infimum into supremum, and now we have a conjugate kind of term here. So we have so to write it in a conjugate form, we have minus a transpose new transpose x minus f of x. Right, we have y transpose x minus fx form. This is f star of, sorry, it's minus a transpose new whole transpose minus a transpose new. So this is our new problem, and this is an unconstrained problem because so we frame the dual, and there are no more constraints anywhere. So this is an unconstrained problem, and the original problem, so solving the original problem will be is equivalent to maximizing this. maximizing this problem because the optimal values are the same. The dual optimal is the same as the Primal's optimal. So we can just maximize this and obtain our Primal's optimal. Move on to the Newton's method with equality constraints. So this is similar to the unconstrained Newton's method. The only difference is, like, there are two differences. First difference is that the starting point should be feasible. And the second one is that the definition of Newton's step is delta x and t is different. So the definition, the previous, in the unconstrained case, we had this definition. In the unconstrained case, we had delta x and t minus del square fx del fx inverse. Actually, this is inverse del fx, right? So how do we move on? How do we go on defining delta x and t when we have constraints now? So the problem we are solving is this main problem. Main problem is to minimize fx subject to ax equal to b. Okay. So the in the similar way that we did in the way that we did in the unconstrained case, similar to that, now we minimize the second order Taylor series approximation of this function. I mean at a point the proximity of x. So if the point is v, then the problem now we are solving is to minimize f hat x plus v subject to a x plus v equal to b, where f hat, or rather I just sorry f hat is the second order Taylor approximation of fx at v. I mean the second order Taylor approximation at x plus v. So now what we do is we the optimal v is the step, right? The step will be the optimal value which minimizes our function at the next step. That is the optimal step, right? So if this is an optimization problem now. So v star, that is this optimal value of so what I want to say is delta x and t in this case, in the constraint case, is defined as v star of this problem, right? So we had some explicit expression for x and t in the unconstrained case. Let us try to find if we have something like that in this case as well. So for that we will use the quadratic program that we just solved. We have a similar formation here as well. So we can just write down the KGT conditions in the matrix form that we did in the dummy problem. This will be del square fx A transpose A 0 del xnt W equal to minus del fx 0, where W is the dual optimal. Okay, now two important points. First is that, so this is the definition and basically the characterization of Newton's step. Okay, we'll expand this matrix and write this in the full way. We have A delta xnt equal to 0, and we have del square fx delta xnt plus A transpose W equal to minus del fx. This is just the expansion. So two important points. First is that Newton's step is defined only at points where KKT matrix is non-singular. Newton's step is defined only where this is the KKT matrix, this matrix, coefficient matrix. And the second point is that when the problem is quadratic, that is actually when the problem is quadratic, the delta xnt solves this optimization problem. Solves actually it solves so delta xnt is solving a problem. So when the problem is quadratic, this quadratic approximation is no more an approximation, it is the actual quadratic itself. So in that case, this f hat x plus v, which is an approximation, that actually becomes the actual function f of x plus v equal to the function. So when the problem is quadratic, delta xnt solves the actual f of x plus v. Another way to look at these two expressions, and that is by solving the actual KKT conditions of the problem which we are interested in, and approximating and running an approximation. So we can so we see that comes out to be exactly this thing. So what I'm trying to say is, this is our original problem. Suppose if we have minimize fx subject to ax equal to b, this is our original problem. And suppose x star is the optimal of this problem, so we have ax star equal to b because x star is feasible. And the second KKT condition is that nu star equal to 0. Nu is the dual optimal. So in our case, instead of, if we replace x star by x plus delta xnt, that is our previous step plus the delta step, what we have is So this thing should be exactly equal to b, because whether it is x or x plus delta x and t, both of them have to be inside the feasible set. So we already know that ax equal to b. This is from the constraint. So we get a delta x and t equal to 0. This is something we get from here. And the second part, that is this equation. Uh, so we replace. Let me write this here. So we replace x star by x plus delta x and t. What we get is uh, del f x plus delta x and t plus a transpose. Nu star is replaced by w. Almost equal to 0, because x plus delta x and t is it's not the optimal, it is on the way of reaching optimal, it is not the optimal point. So we have this thing. Now the first order approximation of this term f of x plus delta x and t, that if we write down the first order approximation of f of x plus delta x and t here, what we have is this. We have del of f of x plus del fx delta x and t, right, plus a transpose w equal to 0. This is the first order approximation, fx plus del fx times delta fx and t, delta x and t, and this is del fx plus del square fx delta x and t plus a transpose w equal to 0. This is an approximation, so we are equating that approximation to 0. So we can see that this is exactly the thing that we got. Talk about the Newton's decrement. So the Newton's decrement in the unconstrained case, it is the same here. It was delta x and t transpose del square fx delta x and t to the half. So in the unconstrained case, we use this metric for stopping and all, because this not metric, this measure, because this got smaller and smaller as we came closer to the optimal point. But now that we have changed the definition of delta x and t, now we have a constraint as well. We have to check if this definition works. So for that we find the distance between our present value and the value after the optimal jump. So the value after the optimal jump is this, right? Where the optimal jump is delta x and t, right? So so minus infimum of, rather f hat of x plus delta x and t, right? And this was delta fx minus write the expression for this thing. This is f of x, the second order Taylor expansion, plus del fx transpose delta x in t plus half del x in t transpose del square fx delta x in t. This is fx minus del fx transpose delta x in t minus half of, this is what we have defined as our lambda here. This is lambda square, so this is lambda square and this thing del fx by our condition, the this condition, no by the sorry this by the definition of del x into, yeah, this condition, the second condition, we can plug that definition here. So that definition is del fx equals minus of del square fx delta x in t plus A transpose W. That is, after plugging this value, we have del square fx delta x in t plus A transpose W times delta x in t whole transpose minus half lambda x square, and this is, if we take this transpose inside, we have W transpose A times delta x in t plus del square fx delta x in t transpose minus, which is just sorry, that was incomplete, plus delta x in t transpose del square fx delta x in t plus, yeah, minus half lambda x square. Now A delta x in t is 0 by our second condition, so this term goes away, and what we are left with is lambda x square over 2. This is lambda x square. So it is still a valid it still gives the sense of distance, like lambda x square by 2, this value, this still gives the sense of distance between the optimal point and the point we are at the present iteration. So we can still use it as the stopping, we still use it for the stopping criteria, like we did in the unconstrained case. A property called affine invariance in the unconstrained case. Let us see if it holds in the constrained case as well. So because the definition of set is changed now, we have to check if the affine invariance holds under this new definition as well. So the original optimization problem that we had is to minimize fx subject to ax equal to b. Now let us take a modified problem in which we transform the variable with t, and we have this as the new constraint. Okay, now we can write down the So what was the KKT matrix in the KKT condition in case of the original problem? The original problem had this KKT condition: A transpose 0. This is delta x nt. This is W equal to minus del fx 0, right? And uh, so now we write down the we write down the same condition for the conditions for a modified problem. So the modified problem is, so the modified matrix will be like del square of oh, we would need the uh, second derivative of this function f of t y, and second and first. So let us, so that is just so del of f t y is just um, rather I should write this like this. We have f bar of y is f of ty, del of f bar of y is equal to t transpose del of f of ty, and del square f bar y is equal to t transpose del f ty t square. Okay, so now we can plug in these values here. So now we have the new matrix S t transpose del square f ty t, and we have at here, we have um, t transpose a transpose here, and the w is unchanged because we made the change only to x. In fact, we changed the variable x from x to ty, so w is unaltered, but our value, this gets changed, and this is minus t transpose del f ty 0. We should move this. Okay, just uh, expand this matrix, and we can see that uh, the del xity that we had is just t times del y in t. If we compare this with the original KKT conditions, so this says all. So this says it all. Like um, even if we have a new definition of del x and t, still the invariance property holds. That is, changing the variable with a linear transformation, uh, it it just makes a change, it just makes the same linear transformation in the step. Quickly write down the algorithm, and we'll move to the convergence analysis. So algorithm, um, so first step, uh, so before starting the loop, we choose a point x which is in the feasible set, and then we start the loop. So we have repeat. um, so first compute the step and the decrement, and stopping criteria. Stop if lambda square by 2 is less than or equal to epsilon. Epsilon is some uh, is the cutoff value where we have to stop. uh, and line search for t. The last step is to update the value of x. um, so so whatever value of x we are going to choose, that is going to be inside the feasible set. Suppose if x2 is the new value and x1 was the old value, right? So what is it really in the, so we can just check if this x2 is really in the feasible set. So we have this uh, relation here, and a delta x and t is 0. So, and this is equal to b, so we have ax2 equal to b. So it is still inside the feasible set, and we are never moving out of the feasible set because uh, starting from the first initialization we are inside the feasible set. So this is also known as feasible descent method, because of uh, this because we are not moving out of the feasible region. And in the beginning of the video we discussed how a constraint equality constraint problem can be converted into an unconstrained problem by eliminating that constraint. So we try something similar with the problem at hand, and we'll try to build some relations between the unconstrained problem that we build and the constrained Newton method that we already have. So this is what we did. So we had uh, we had so we introduced a matrix F such that f dash z equal to f z plus x hat. X hat is a particular solution of ax equal to b, and yeah. So from the so now the unconstrained problem is to minimize f hat z, which is equal to f of fz plus x hat and no other constraints. So the gradient of f hat z is equal to, we'll need the gradient and the Hessian. So gradient is plus and the Hessian. Hessian is f transpose del square f fz plus x hat f. Right. So now the So the Newton step. So now this is an unconstrained problem, and we can define the Newton step for this unconstrained problem. Newton step for this problem is delta ZNT equal to minus del square F Z inverse del F Z. This is from the expression of the unconstrained step. And now if we substitute the f hat z with what with the actual f, we immediately get this to be minus f sorry minus f transpose del square fxf inverse f transpose del fx, where x is equal to fz plus x hat, and yeah. Now if delta ZNT is same as the search direction, is the same search direction as delta XNT. To see this fact, that is delta XNT is same as F delta ZNT, what we have to do is just plug in this into the KKT conditions and verify that it is true. So these are the conditions: delta XNT plus A transpose W plus del Fx equal to 0, and A times delta XNT equal to 0. So and we need a particular choice of W for this thing to satisfy, and that choice turns out to be minus A transpose inverse A del Fx plus del square F x delta XNT. So we can see that this gives the desired result. So we can just plug in that value. We have del square fx f delta ZNT plus A transpose W plus del fx. This, so we evaluate this term, it should come out to be 0. This negative can be taken out here, and this is A transpose inverse A. So this is A transpose inverse, so this is this thing, A transpose inverse A inverse A times this thing. This goes away because it is identity, and this term cancels out with this term, and these also cancel out, so this gives 0. Then second term is A delta XNT, which is A times Z times delta, sorry, A times F times delta ZNT, and AF is 0, so AF is 0 by construction of F, so this is 0, and so both the conditions hold. Now so the Newton step Newton's step is Newton's step in this case, in the unconstrained cases, uh, is the same. Now, what about the Newton's decrement? So Newton's decrement is, so this is the expression for Newton's decrement in the reduced problem. And um, this is the second derivative of the so this is a Hessian of uh, the new variable, and this is just f transpose del square fx f delta z and t. So this is f times delta z and t, which is delta x and t. So this is delta x and t transpose del square fx delta x and t, which is the same as lambda x whole square. So we have so the Newton's decrement also come out to be the same. So what we want to say is that the constraint problem is the same as the reduced problem. Like the dynamics, the working dynamics is the exact same, because all our dynamics depend on only these two values, and they both of them are same. So we can analyze this constrained Newton's algorithm using only the unconstrained case. The analysis, we can just take some results from the analysis of the unconstrained case and plug them in here, and we can see what is happening here. But for that we need to prove one more implication. Uh, now that the two problems are almost equivalent, uh, we have to establish the equivalence between the conditions under which they converge. So convergence. So the assumptions under which uh, the convergence analysis is carried out for this constraint problem, these are the assumptions. So f is a closed function. Second assumption is that on the set S, Hessian is upper bounded, and the second norm of this matrix is upper bounded by k. So second norm of the matrix means that second norm of the matrix equals to the largest singular value, sigma max, and that is upper bounded by k. And the third assumption is the Lipschitz condition. So there we have Lipschitz condition over the objective function. So we need to establish that these conditions are equivalent to the conditions that we have that we saw when we were analyzing the convergence of an unconstrained problem. So So if we write down those conditions, they were the so there are so this was is those conditions are this one was there. So the unconstrained problem is now the I mean the problem that we have converted into is an unconstrained problem. So these things should hold particularly. So we have uh, Hessian upper bounded by some m, and then this is lower bounded by some m. That is, this is the uh, strict convexity, strong convexity assumption, and the F tilde and the Lipschitz condition. Minus del square of x tilde should be less than equal to some value L tilde z minus, sorry, this is z minus z tilde okay. So these three conditions imply these three conditions. That is what we have to prove. So we start with the first one. This is what we have to establish, right? So we can simply write down the Hessian of f tilde, and this is just f transpose del square f of fz plus x tilde times f, right? F this is fz plus x tilde, right? That's how this comes. And so the second norm of Hessian, this is like, it is sufficient to prove that this is less than equal to some value m tilde. Rather, I will write this. This is sufficient to prove that this thing holds. So this is equal to f transpose del square f fz plus x tilde f, and by Cauchy-Schwarz I have this by Cauchy-Schwarz, and I have this condition that this is the first condition. By the first condition I have that the Hessian of objective is bounded. So this is my Hessian of objective and this is bounded. So this is less than equal to the second norm of f times m. So this is just some m tilde. This is a finite value, so this is just some m tilde. So del square f tilde z is the Hessian is bounded by Mi. Okay, the Lipschitz condition. So this is what we have to establish for some L tilde. This holds, and so we can just write down the definition of yeah, we can write down the definition of F tilde. So we have um, F transpose del square Fz plus x hat F minus F transpose del square Fz plus x hat z tilde. This thing I can take out the F transpose and F by Cauchy-Schwarz. So I have this value times and now I can apply the this is the objective now. This is the objective of the constraint problem, and I have already been given that this is Lipschitz constraint. So I mean this is this F follows Lipschitz condition. So we have this thing less than equal to some L and Fz plus x tilde minus Fz tilde plus x hat which is equal to Fz minus Fz tilde again by Cauchy-Schwarz. I have one more F outside. So this is L tilde. So that's it. Third implication is that this condition that for the objective of our problem, if it is the Hessian is bounded and this that the inverse of KKT matrix inverse of the singular value of that inverse is bounded by K, then if we have these two conditions, then we have this. So we have strong convexity for the objective of the reduced problem for some that is the Hessian is greater than equal to Mi for some M. So I'm not proving this here, it is there in the book. So So these three conditions together, they give um, the analysis for convergence of the constraint problem with an equality constraint. What we did is we converted it to the unconstrained problem with f tilde, and f tilde, and we saw that these three things are what we require to um, analyze the convergence of an unconstrained problem. These three things, these Lipschitz condition, and the strong convexity, and the boundedness. The so the analysis is as it is similar to the unconstrained problem.